Well, hello there. Chapter 23 is what we're going to do right now. Section 23, a few inferences from the general principle of relativity. We're just one day from winter solstice when the sun is resurrected to longer days. And so it may actually start getting warmer and have more sunlight, which is kind of nice. Because it's been pretty cold where I'm at for quite a while now. Cold and rainy. Okay, so the good news for you people out there who are allergic to math. I'm not allergic to math. Actually, I'm addicted to math, kind of. But I know this chapter doesn't have any equations again, and it's 2, 3, 4 pages about. So I'm just gonna try to read and comment, and we'll see as we go along. Um, and hopefully we can learn something here. Okay, so this is chapter 22, a few inferences from the general principle of relativity. So inference, Alexa, define inference. Alexa, volume 10. Alexa, define inference.
Inference is usually defined as the act or process of inferring, deriving by reasoning. For more, ask me to give you more definitions for inference. The mic's back on.
Okay, so just from the title, it looks like Einstein just saying, okay, there's some things that are related to relativity or infer from relativity that give us some insight. He's saying, I think, in this section. So, okay, I'm going to go ahead and read. The considerations of chapter 20 or section 20 show that the general principle of relativity puts us in a position to derive properties of the gravitational field in a purely theoretical manner. Let us suppose, for instance, that we know the space-time course, quote-unquote, course for any natural process whatsoever as regards the manner in which it takes place in the Galilean domain relative to Galilean body of reference K. So remember, K is the fixed reference. By means of purely theoretical operations, as an example, or to say simply by calculation. We're then able to find out how this known natural process appears as seen from a reference body K prime, which is our moving reference body, which is accelerated, goes fast, relative to K. But since a gravitational field exists with respect to this new body of reference K prime, our consideration also teaches us how the gravitational field influences the process studied. For example, we learn that a body which is in a state of uniform rectangular motion with respect to K, in accordance with the law of Galileo, is executing accelerated, it goes really fast, in a general curvilinear motion with respect to accelerated body, reference body K prime. Okay, now he's talking about the chest in space with the rope and everything, or like the box in space. The acceleration of curvature corresponds to the influence on the moving body of the gravitational field prevailing relative to K prime. It is known that a gravitational field influences the movement of bodies in this way, so that our consideration supplies us with nothing essentially new. However, we obtain a new result of fundamental importance when we carry out the analogous consideration for a ray of light with respect to the Galilean reference body K. Such a ray of light is transmitted rectilinearly with velocity c. It can easily be shown that the path of the same ray of light is no longer a straight line when we consider it with reference to the accelerated chest referenced by the K prime. From this we conclude, in italics here, that in general, rays of light are propagated curvilinearly in gravitational fields. In two respects, the result is of great importance. So what he's saying here is like, let's just pretend I'm gonna have to use a square for a star. Let's pretend this is a star. It's supposed to be round. Most interesting thing about nature seems to like circles, but we got a square today. But this is like a star, and so imagine this is like a ray of light shooting from the corner of your screen right there, and a ray of light goes by the star, and then it bends around the star because the star's got this gravitational field. So it warps the space around the star, which is kind of interesting. Why? How that happens? I don't know, but that's what they say. Uh, and the first, well, I think it's because it's warping the star. The gravitational field supposedly warps the space around it, and by warping the space uh, with a ray of light, so it's actually kind of like almost like a straight line because even though the space is warped around the star, so it's getting kind of interesting, kind of mythological, like almost, but it's science based. So it's actually observed. So it's not even mythological because they've observed this with stars and objects behind the stars or in front of the stars, and they've actually measured the light getting bent by the gravitational field around the star, and that's one of the things that actually one of the experiments that proved Einstein's this book what Einstein said in here, because it's an observation that's consistent with no counterexample known presently. Um, okay, so I'll read on the next paragraph here. In the first place, it can be compared with the reality, although a detailed examination of the question shows that the curvature of light rays required by the general theory of relativity is only exceedingly small for the gravitational fields that are disposable in practice. Its estimated magnitude for light rays passing the sun at grazing incidence is nevertheless 1 minute 7 seconds of arc, or 1.7 seconds of arc, something like that. This ought to manifest itself in the following way. As seen from the Earth, certain fixed stars appear to be in the neighborhood of the sun and are thus capable of observation during a total eclipse of the sun. At such times, these stars ought to appear to be displaced outwards from the sun by an amount of indicated above, this 1.7 seconds of arc, as compared with their apparent position in the sky. When the sun is situated at another part of the heavens, the examination of the correctness or otherwise of this deduction is a problem of the greatest importance, the early solution of which is to be expected of astronomers. And there's a footnote here. By means of the star photographs of two expeditions equipped by a joint committee of the Royal and Royal Astronomical. See, these are the people that observed what Einstein predicted. Astronomical societies, the existence of the deflection of light demanded by a theory was confirmed during the solar eclipse of May 29th, 1919. Common error, common error. CF Appendix 3. I was referencing Appendix 3. So. In the second place, our results show that according to the general theory of relativity, the laws of the constancy of the velocity of light in a vacuum, which constitutes one of the two fundamental assumptions in the special theory of relativity, into which we have already frequently referred, cannot claim any unlimited validity. A curvature of rays of light can only take place when the velocity of propagation of light varies with position. Now, we might think that as a consequence of this, the special theory of relativity, and with it the whole theory of relativity, would be laid in the dust. But in reality, this is not the case. We can only conclude that the special theory of relativity cannot claim an unlimited domain of validity. Its results hold only so long as we are able to disregard the influences of gravitational fields on the phenomena, as an example of light. Since it has often been contended by opponents of the theory of relativity that the special theory of relativity is overthrown by the general theory of relativity, it is perhaps advisable to make the facts of the case clearer by means of an approximate comparison. Before the development of electrodynamics, the laws of electrostatics were looked upon as the laws of electricity. At the present time, we know that the electric fields can be derived correctly from electrostatic considerations, only for the case which is never strictly realized, in which the electrical masses are quite at rest relative to each other and to the coordinate system. Should we be justified in saying that for this reason electrostatics is overthrown by the field equations of Maxwell and electrodynamics? Not in the least. Electrostatics is contained in electrodynamics as a limiting case. The laws of the later lead directly to those of the former for the case in which the fields are invariably with regard to time. No fairer destiny could be allotted to any physical theory than that it should of itself point out the way to the introduction of a more comprehensive theory in which it lives on as a limiting case. In the example of the transmission of light just dealt with, we have seen the general theory of relativity enables us to derive theoretically the influence of a gravitational field on the course of natural processes, the laws of which are already known when a gravitational field is absent. But the most attractive problem to the solution of which the general theory of relativity supplies the key concerns the investigation of the laws satisfied by the gravitational field itself. Let us consider for a moment. We are acquainted with space-time domains which behave approximately in a quote-unquote Galilean fashion under a suitable choice of reference body, as in, to say domains in which gravitational fields are absent. If we now refer such a domain to a reference body K prime, remember K prime is the moving reference frame. K prime, any motion, then relative to K prime there exists a gravitational field which is variable with respect to space and time. And then there's a footnote here. This follows from a generalization of the discussion in chapter 20 or section 20. The character of this field will of course depend on the motion chosen for K prime. According to the general theory of relativity, the general law of the gravitational field must be satisfied for all gravitational fields obtainable in this way. Even though by no means all gravitational fields can be produced in this way, yet we may entertain the hope that the general law of gravitation will be derivable from such gravitational fields of a special kind. This hope has been realized in the most beautiful manner, but between the clear vision of this goal and the actual realization, it was necessary to surmount a serious difficulty, and as this lies deep at the root of things, I dare not withhold it from the reader. We require to extend our ideas of the space-time continuum still farther. And that's the end of this section or chapter. Next one is chapter 23 or section 23, behavior of clocks and measuring rods on a rotating body of reference. So I put a comment in the previous video that showed like a black and white video of these scientists with a little table, and the table's rotating, and they kind of move the ball or move the top or whatever it is, sliding on the table. It's really interesting. I highly recommend you watch it. I think I saw that video as a kid in elementary school. So, so this chapter seems to. What did we learn? Did I learn anything? Did you learn anything? A few inferences from the general principle of relativity. So, I mean, it looks like. I mean, he's talking about how the gravitational field influences the propagation of light through space, and he kind of leads into space time. So yeah, it's there was an actual experiment done to verify this, and it's talked about in the footnotes. And let's ask. Let's ask Google. Hey Google, tell me about the Royal and Royal Astronomical solar eclipse of May 29th, 1919.
On the website earthsky.org, they say, bottom line, the solar eclipse of May 29, 1919, was the day astronomer Sir Arthur Eddington verified Einstein's general theory of relativity by observing how stars near the sun were displaced from their normal positions.
Yeah, so So this is an observation. Uh, that space is being warped. Space is being warped uh, around uh, star, the sun, the gravitational field, and don't forget it's solstice coming up on Earth, which has to do with the sun. Um, so the sun warps the space around it, and such that uh, I mean, when you shine a light, it's almost like a lens. It's like a it almost seems like it. It's like a lens because the lenses bend light. Uh, you can have like a convex lens or a concave lens. I forget which one bends out, and which one bends in, but um, which is truly amazing because it's like okay, a gravitational field is warping space so that it creates a lens effect, and so yeah. I mean, I wear glasses. Okay, so it's almost like the glasses. These are like I need to get a new pair of glasses, but these are all screwed up. But when the light shines through it, it gets warped because it actually gets bent a little bit. And if I had a magnifying glass, I'm gonna have a magnifying glass, but I'm too lazy. It's like only 10 feet away. But so it's interesting because so it's like supposedly gravity is warping space. Uh, it's like this just pretend this is a rocket ship, and it's like it's warping space a little bit different than the bottom of the rocket as opposed to the top of the rocket, and that pulls the rocket down to Earth. And yeah, it's pretty amazing stuff. So, anyways, I hope you learned something, and I hope you have a good solstice tomorrow. I think on the northern hemisphere it's called winter solstice. Right now I'm in the northern hemisphere. If you happen to be in the southern hemisphere, it'll be summer solstice for you. So your days will get shorter, uh, and nights longer. But I'm in the winter solstice, which means that tomorrow's winter solstice. So the days will start getting a little bit longer, and yeah, that's all. The kind of the calendar was. They tried January 1st should probably really fall on solstice, but then it has to move around all the time. But you're always trying to adjust the calendar, I guess. I don't know if you've heard of leap year, but February is like a month where they have a leap year. But all right, you take care of yourself, and you have safe, fun time. I hope you maybe can light a candle for solstice or something like that. You take care of yourself, and have a good time.